I'm Sharyuan, and in this talk, I will explain the key insight behind GCS star, our algorithm for forward heuristic search on implicit graphs of convex sets. Many robotics problems involve making discrete and continuous decisions jointly. For example, collision-free motion planning selects whether to go left or right around an obstacle, along with the continuous trajectory to do so. In manipulation, we choose which side to push an object from, as well as what continuous direction to push it in. In task and motion planning, the sequence of actions, like first grasp the hook and then hook the block, are discrete choices, and continuous parameters like where to grasp the hook affect both the cost and feasibility of that action sequence. In this work, we focus specifically on tackling large-scale, implicitly defined problems, meaning problems that are so big that you never want to explicitly write the whole thing down. To that end, we apply our method to simplified planar pushing because it is the poster child for combinatorially exploding discrete continuous problems. One family of approaches involves discretizing and using discrete graph search, but the real world is continuous, so that can be limiting. On the other end of the spectrum, we have methods like trajectory optimization that are able to easily enforce continuous constraints and work well locally, but that are notorious for local minima and poor exploration. And then we have sampling-based methods like RRT and sampling-based task and motion planning algorithms. These tend to be probabilistically complete, but as the dimension increases, it can be hard for your samples to cover this space sufficiently. Our contribution is a method that combines graph search and convex optimization to solve these large planning problems. In this talk, I hope to convey the answers to these three questions. Why use this approach? What problem do you run into? And how do you fix it? More specifically for the first question, why combine graph search and convex optimization to solve these problems? But first, I need to say a bit more about how we can even do this. We can start with a problem modeled as a discrete graph, but to better handle continuous aspects of the problem, we can associate with each vertex a convex set, and what we end up with is a graph of convex sets. Our discrete choices are modeled as choosing which edges to take, and our continuous choices are modeled as choosing a point in each set. For a fixed discrete path, we can use convex optimization to solve for the continuous trajectory of points. So finding a solution to the planning problem becomes equivalent to finding the shortest path on the graph of convex sets. In this formulation, we can add convex costs and constraints on each edge. For example, points coupled by the black edge are constrained to lie in the dashed regions. Note that the edge constraints can affect the feasibility of discrete paths, and the cost shown in the green gradient is a function of the position of the points. The original approach to solving these problems using the convex relaxation becomes intractable when the graph is too large to even fit in memory. Two recent papers propose methods for doing A star on graphs of convex sets. While this helps them scale better than the original approach, they are not designed to handle cases where the edge constraints can make paths infeasible. We use INSAT x GCS star as a baseline in our experiments. The thing is, many robotics problems have both really big graphs and many action sequences that are infeasible due to constraints. For example, with just 5 bodies in the problem on the right, we get approximately 10 to the 9 vertices and up to 10 to the 17 edges. So why combine graph search and convex optimization? The first and I think most important part of the answer is, when we're searching over the complex space, the discrete informs the continuous. Once you fix the discrete decisions, your continuous decisions become convex and easy to optimize. And the continuous informs the discrete. Optimizing the trajectory for a particular path will tell you quickly and with certainty whether it is feasible and give you its cost, which can guide the discrete search. The second key thing enabled by this approach is that it does not require explicit construction of the graph. We can just start with the source and a getSuccesses operator that gets the successes of any vertex you pass in, and work with that. This opens up a whole different class of problems that we can now solve, because your search space doesn't even need to be finite. The next 3 points assert that we can largely hold on to the strengths of A star. That is, we can retain some sense of its cost optimality and completeness guarantees. We can make the search effort proportional to the query difficulty instead of always having to consider the whole graph even if the query is really simple. And finally, just like in weighted A-star, if we're willing to accept some level of suboptimality, we can inflate our heuristic so the algorithm becomes more greedy. So I've answered the first question, why use this approach? Now I'll explain what breaks down when applying discrete A-stars domination checks for pruning paths. The short answer is that we will lose cost optimality and completeness, which naturally leads to the question, how do we modify the domination checks to retain these properties? We're going to do a deep dive into a 2D toy problem that makes the issues easy to visualize. Suppose a robot is tasked to hop from source S to target T, minimizing the Euclidean distance of the path. On the left, the robot is restricted to hopping between discrete points. This takes the form of a traditional graph search problem. On the right, we have convex stepping stones, and the robot can hop to any point within each stepping stone. This takes the form of finding the shortest path on the graph of convex sets. In discrete A-star, we only need to keep track of the single best path to reach each vertex. Since the pink path is longer than the blue one, we can safely prune the pink path. This pruning is what makes the algorithm efficient. On the right, if we try to do the same thing, we run into a problem. The cost to reach C through pink is higher than through blue, so we might think that we can prune pink. But the optimal path to the target goes through the pink path, so if we pruned it, the algorithm wouldn't return the optimal path. Let's take a second to understand what went wrong. Intuitively, the set D being at the bottom means that every path to the target will have to take a detour towards the bottom. And so the pink path that better accommodates that future detour, even though it takes a longer path to reach C, ends up being more efficient than the blue path that greedily tried to reach C as quickly as possible. So we want to know under what conditions on the paths we found to reach C, we can prune the pink path. I'll spin things around so it's easy to see how the position in C is the domain of the cost to come function. The curves show the cost to come to each point in C via the blue and pink sets respectively. There are no edge constraints in this graph, so both paths can reach every point in C. Since all edge costs are convex, the cost to come through a fixed path will also be a convex function. The blue dash trajectory is the one that minimizes the cost to reach C, marked with the star. So, when might a path be part of an optimal path to the target? The answer is if there exists some point that is reached with lower cost than all alternate paths found so far. The points in gray satisfy this condition, so we cannot prune pink. To go back to the question of what broke down, the minimum of blue is less than the minimum of pink, which is why we thought we could prune pink, but that doesn't account for the fact that future costs might make it better to reach other points in C. The best we can do is make sure that for any point in C, we don't prune a path if it's the best way we know how to reach the point. Now, we will see how edge constraints can make us lose completeness. In this example, points coupled by the edges are constrained to be axis aligned, as denoted by the orientations of the black arrows. We see that the blue is the shortest path to C, so we might be tempted to prune the pink path. But if we did that, we wouldn't find any feasible path, because blue can't reach high enough in C to come straight down to the target. Sweeping out the regions in C reachable by the blue and pink paths, and the backward reachable region from the target, in other words, the points in C from which the target could be reached, we see that only pink overlaps with the orange. But when searching forward from the source, we don't know the region in C backward reachable from the target. So that information cannot come into play when deciding whether to prune. Looking at the cost to come, the region of C that can't be reached by a path has cost to come of infinity. The pink reaches this region in C with costs lower than infinity. And so according to the principle that we derived earlier, we cannot prune it. And this preserves completeness of our algorithm. So we've answered the second and third questions. We have two possible implementations. In the first, we evaluate the domination condition at samples. This only gives you probabilistic guarantees, but is faster and works well with few samples. In the polyhedral containment implementation, we instead compare the epigraphs of the cost to come via different paths, which are themselves convex sets. Here we have exact guarantees, but it is significantly slower than sampling, and for now only works with linear costs and constraints. To focus on the combinatorial explosion of contact modes, we show results for simplified planar pushing, where we have polyhedral bodies, no rotations, and no friction between the bodies. These solutions were found using the variant of our algorithm that has probabilistic guarantees and uses an epsilon inflated heuristic. We compare to IXG star as our baseline. Our solutions are found in 3 seconds, 38 seconds, and 22 seconds respectively. Notice how in the task on the right, the robot uses objects to push each other in a chain, as well as contact with the static obstacle to slide the objects towards the goal, and then pushes all three down at the same time. In the middle task, even though the graph is smaller, the solution is more complex. It has to push the object through the narrow gap, make just enough space for it to squeeze itself around the object, come back around, push the object back towards the obstacle in order to use the obstacle to push it vertically straight up. So there's no way trajectory optimization would find solutions like this, and a fully discretized version of the problem would lead to even larger graphs. Finally, limitations. Just like other informed search algorithms, performance heavily depends on the strength of the heuristic. Our implementation with exact guarantees needs more work to be extended to nonlinear but still convex cost and constraints, and is too slow to be used on the really large problems, although these limitations don't apply to the probabilistic versions. And finally, unlike A star, GCS star is not optimally efficient. Thanks for listening. We'd love for you to read our paper and understand all the things we didn't have time to cover today.